Okay, so let's talk about carbohydrates. So carbohydrates are what the name says, it's carbons that are hydrated. So hydration is adding H2O molecules to something. So carbons with H2O molecules. So the formula, so CnH2nOn. So for each carbon you have a H2O molecule attached. So the carbons range from 3 to 8 carbons. So it's a major class of biomolecule and there's a wide variety of roles. So examples include providing energy, so a fuel source, a structural role such as cellulose in plants, recognition molecules, so carbohydrates are usually attached to proteins or lipids or cell surfaces and they act as recognition molecules. So other molecules bind to the carbohydrates and then it starts a series of biochemical reactions. So there's quite an interesting area of drug design, and that's designing things that bind to these recognition carbohydrates. Okay, so Institute of Glycomics at Griffith University specialise in sugar chemistry. So there's a very, very big following for carbohydrate chemistry. And we're very lucky to have Stephen Lavonis working at Bond University, who is a carbohydrate chemist. So carbohydrates can be monosaccharides, disaccharides or polysaccharides. So they can have one sugar, so monosaccharide, two sugars, disaccharide, polysaccharide, many sugars. They can be linear or cyclic. So when they cyclize, they form hemiacetals. So here is a linear structure. Okay, so we've got an aldehyde and it's going to cyclize onto this OH here, and we're going to have the loss of that proton. So we can have this occurring from either the front or the back side attack, but what you're going to end up with is an anomeric carbon that is bonded to a O that's bonded to another R group, and it cyclizes around like that. So we've got a COR, and that C also has an OH, and that is our hemiacetal. We can have alpha or beta hemiacetals. So alpha is when the OH is down, and beta is when the OH is up, when they're drawn in the Haworth projection way. So this is what we call the Haworth projection way of drawing monosaccharides. So monosaccharides can be polyhydroxyaldehydes or ketones. Okay, so they can have an aldehyde or ketone moiety on them. The simplest sugars examples include fructose and glucose, so 1 sugar units, and the nomenclature is based on the number of carbons ranging from 3 to 8 and the type of functional group that each of those carbons have. So for example, a 3-carbon sugar would be a triose, 4-carbon sugar would be a tetrose, 5 pentose, 6 hexose, 7 heptose, and an 8-carbon sugar would be an octose. They can have an aldose or a ketose, so an aldehyde or a ketone. They can be linear or cyclic, so usually they're based on a pyranose or a furanose ring. So a pyran is a 6-carbon with an oxygen in it, and a furan is a 5-carbon with an oxygen in it. So the oxygen's replacing one of those carbons. So we've got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. There can be D and L nomenclature, and the D form is the biologically active form. So let's have a bit of a further look into monosaccharides. So there's different ways of representing them. Like I mentioned before, you can have the Haworth projection, which looks like this, and that one there is your anomeric carbon. Okay, your anomeric carbon is a chiral carbon, and that is where your stereoisomers are indicated. You can have your Fischer projection, which is your flat projection like this, so like we had on the previous slide. And what that means is that these ones are going into the page and these ones are coming out of the page. So the Fischer projection means this. So we've got them coming up into the page and these ones coming out of the page. So if we were to draw them with some models, we would have this structure here. So they're not flat compounds, they've actually got some three-dimensional shape to them, although we represent them by drawing a flat compound. So this one here is saying that these fat ones are coming out towards you and the lined ones are going into or are in the plane of the whiteboard or the page that you're looking at. So like I said before, so if you have the anomeric carbon with the OH going down, it's alpha, and if it's going up, it's beta. Okay. So when you are in your boat or chair conformation and you want to look for an alpha, you have your OH in the axial position and your beta would be in the equatorial position. So in the boat or chair conformation, your axial anomeric carbon is representing alpha and your beta is represented by being in the equatorial position. Another way of representing it is our D and L. So if we draw them in our Fischer projection and we look at the OH that's on the central carbon here, so we have our aldehyde at the top and then we have our CH2OH at the bottom, and then we look at the one carbon that's up and we look at this OH, and if it's on the left it's an L, and if it's on the right it's a D sugar. Okay, so let's try this example here. So looking at the carbon up from the CH2OH, so on the left it would be a L and on the right it would be a D. Okay. So converting from these structures is quite challenging. So in this course we'll be focusing on converting from Fischer to Haworth, and next when you go into biochem you're going to have to go from Haworth into chair. I will give you an idea of how to do that, but this will not be examined in this course. So when we're looking at Fischer and we want to go to Haworth, we have to count our carbons. So this one has an aldehyde at the top, so that's 1, 2, 3, 4, 5, 6 carbons. Okay, so the reaction occurs between the carbon 1 and the oxygen on carbon 5. So it's this one here and this oxygen there. So they're going to cyclize to close the ring. So when you draw it, that's your first carbon, so this one here. And then you've got your second, third, fourth, fifth, and then you've got your CH2OH that comes off your fifth carbon. So right hand side is down, left hand side is up. So if it's on the right hand side, it's going to be down, and the left hand side is going to be up. So we've drawn our structure in, done a squiggly line for this OH because it's going to be a racemic mixture. Our second carbon, so it's on the right hand side, so we draw it down. Our third carbon is on the left hand side, so we draw it up. Our fourth carbon is on the left hand side, so we draw it up. And our fifth carbon is on the right hand side, but this one has been reacted. Okay, so our OH has been reacted here, so we don't draw it in, and the only place for that CH2OH to go, because it's so bulky, is in the upwards position. So when you go from Haworth into the chair, you need to look at the downwards facing groups. and the downward facing groups become the bottom of the chair. So your axial, equatorial would be those positions, and that's your axial, equatorial. You'll see they're all of those groups are on the bottom of that chair. And it's quite complicated, and like I said, I just wanted to mention it to you, but we will not be going into this area. So disaccharides are where you have two monosaccharides that are joined together. Okay, they're called glycosides. They're stable in water and they hydrolyze in acidic environments. Okay, so here's your anomeric carbon. In an acidic environment, you will have hydrolysis, so your CH3 group would add on So in an acidic environment, you would have hydrolysis. Your CH3 group would add on to that oxygen, okay, and you would get a CH3 added on like this one. So you'd have a COCH3. And we can use this to add on more sugars. So if you have a monosaccharide and you want to make a disaccharide, you add a little bit of acid and you add in the second sugar, and it will then link together. So it's called a glycosidic bond that's been formed. So this bond here is a glycosidic bond, okay, and we can name that glycosidic bond. So here, this one is in the equatorial position, so it's a beta. In the axial position, it would be an alpha. So in the equatorial position, it's a beta, and it's between carbon 1 and 4. So it's a beta 1,4 glycosidic bond. Okay, so how do these glycosidic bonds form? Let's have a look at the mechanism. So we've got our hemiacetal that we're starting with. We've got an acidic environment. We get the protonation of that OH to make the oxonium ion, which is a great leaving group. We have the lone pairs kick down and kick out that leaving group, and then we have the alcohol that's usually in excess react with that anomeric carbon, and then we get the quenching of that positive charge, and then we have the deprotonation to form our glycoside. So our glycoside is an acetal. So we started off with a hemiacetal, and now we have an acetal. So carbohydrate polymers are directional. So like most other biological polymers, one end of the chain is different structurally to the other. So the other examples are proteins. You have your C and your N termini, and your DNA, you have your 5' and your 3' termini. So for carbohydrates, you have your reducing and your non-reducing end. So let's have a look here. We've got our reducing end, and that's when we have our anomeric carbon that's available, and we have our non-reducing end when we don't have our anomeric carbon available. So this is the structure of starch, and the polymers are linked in an alpha 1 to 4 form. So this is our carbon, it's going down, so it's an alpha. So this is our Hayworth, so when it's going down it's an alpha, and it's between carbons 1 and 1, 2, 3, 4. So it's an alpha 1 to 4 linkage there. Here in cellulose we have a different linkage. We have the alpha carbon. We have a different linkage. We have the anomeric carbon here that is up, so it's a beta 1 to 1, 2. So it's a beta 1 to 2 linkage now. This is our non-reducing end, and this is our reducing end. So there's some more linkages to show you. So our anomeric carbon, axial, so it's a alpha, and it's 1, 2, 1, 2, 3, 4 linkage. Here we have an equatorial, so it's beta, okay, and it's 1. We've got here, so that's carbon 5, so it's 1, 2, 3, 4, so it's a beta 1, 4 linkage. Okay, so have a go at looking at these ones. So the linkage we have here is we have a axial, so it's an alpha 1, 4. Here we have an equatorial 1, 4. So it's a beta 1, 4. So thank you for listening to my lecture. Sorry my voice has been a bit funny. I'm a little bit unwell on this recording. Any questions, make sure you email me or come visit me in my office. I'm always happy to help.